Application of second-order linear ODEs with constant coefficient. Group 7, Section 2, Lecturer's name, Madam Shahibanun binti Isa. Group members, Ahmed Jafri bin Hussein, AN 240110, Chan Enyong, AN 240014, Nurul Alia binti Muhammad Sufyan, AN 240028, Nurul Farahani binti Karim, AN 240053, Nurin Natasha Najwa binti Zainuri, AN 240055, Siti Nur Afrina binti Hamid, AN 240062. Introduction. 1.1 Background of the differential equations. Differential equations are fundamental tools in modeling various phenomena in engineering, physics, and applied sciences. They describe relationships involving rates of change and are used to predict the behavior of dynamic systems. In particular, ordinary differential equations are equations that contains one or more functions and their derivatives, which relate to a single independent variable oftentimes. 1.2 Background of the second-order ordinary differential equation. Second-order ordinary differential equations involve the second derivative of a function and are essential in analyzing systems with acceleration or curvature. These equations typically arise in systems involving mass spring damper models, electrical circuit, or fluid dynamics. A general form of a second-order linear ODE with constant coefficient is a d square x dt square plus b dx over dt plus cx equals to ft, where a, b, and c are constants and ft represent an external forcing function. The solution to such equation depends on the nature of the roots of the characteristic equation and the form of ft.
Introduction 1.3 Application of the differential equation, motion of the mechanical system. In this project, the application of second order linear ODE is focused on modeling the motion of mechanical system, particularly mass spring damper system. For question 1, we analyze the free damper motion of an object with mass 3 kg attached to a spring with spring constant 16 Newton meter. Displays 0.3 meter for the equilibrium position and realized for rest in a medium with damping coefficient 5. External force in apply in the case. Question 1. Question 1. Motion of the mechanical system, free damper motion, and this is the formula. So A is a air resistant, M is a mass, K is spring constant, and F the external focus. Suppose an object with a mass A kilo is placed up to the lower end of a spring suspended for the ceiling. The object is pulled down B and below its equilibrium position and released at t equal to 0 from rest. Internal velocity is 0. No external focus are presented, but the resistance of the medium is C. Determine the resulting motion X if the spring constant is 16 Newton meter.
Okay, now I'm going to talk about question 1 solution. After we sub a number into it, we can convert it into m squared plus 5 per 3m plus 16 per 3 is equal 0. So from this, you can press calculator to find the m1 and n2. So from this, we can see that it is complex roots. Then we can find the alpha and beta. After this, we sub this into the general solution from the formula. Then we can find that xt is equal exponent power negative 5 per 6t times a cos square root 167 per 6 plus b sine square root 167 per 6t. So after we found the general solution, we can sub the t equal 0 and xt equal 0.3 into it. After we sub t equal 0 and xt equal 0.3 into it, we can find that A is equal negative 0.3. Then next, we want to differentiate the general solution. So here got given t equals 0, x prime t equals 0 also. X prime t is the differentiate of the general solution. So after differentiate, we sub t equals 0 and x prime t equals 0 into it, we can find that b is equal negative 1.5 over square root 167. Then last, we should sub a and b back into the general solution. Then we can find that xt is equal exponent power negative 5 per 6t times negative 0.3 cos square root 167 per 6t times 1.5 per square root 167 sine square root 167 per 6t. That's all from me. Thank you.
Next, we move to question 2.
For question 2, we are given a second order differential equation representing the motion of a spring's mass system subject to an external force. Our task is to find the position of the mass over time using both the method of undetermined coefficient and Laplace transform by applying the given group data for the constants such as mass, damping, and spring stiffness.
Hi, Assalamualaikum. My name is Siti Nafrina binti Hamid. My metric number is AN240062 and I'm going to explain question to 1 undetermined coefficient. So based on the equation, we got my double prime plus ay prime plus ky equal to ft, m equal to d equal to 2 kg, k equal to 4k over m, a equal to f equal to 5, ft equal to et plus 2.3x, and finally we got 2y double prime plus 5y prime plus 4y equal to 2.3x. So for the part 1, we must search for yc. So based on 2y prime plus 5y prime plus 4y equal to 2.3x, we must change that form into the normal equation, which is we got 2m squared plus 5m plus 4 equal to 0. So after that, we must take that equation and put into our calculator to search for m1 and m2. So for m1, we got negative 5 plus 7i over 4, and m2, we got negative 5 negative 7i over 4. And after that, for m1 and m2, we must separate that fraction into two other fractions, which is we got m1 equal to negative 5 over 4 plus 7 over 4i, and m2 we got negative 5 over 4 negative 7 over 4i. So we take that m1 and m2 and we need to choose for alpha and beta number. So for alpha number, we choose for negative 5 over 4, and for beta number, we take for 7 over 4. So why we take that number for alpha and beta is because beta we need to take the imagination number. Okay, so based on that number we got for alpha and beta, we must substitute into formula that we got. Formula is y equal to exponent power of ax, a cos beta x plus b sin beta x, and we must substitute the alpha and beta number into that formula. So after we substitute, we got finally y equal to exponent power of negative 5 over 4x, a cos 7 over 4x plus b sin 7 over 4x.
Kemudian untuk part 2, cari YP iaitu fx sama dengan 2.3x. Berdasarkan persamaan tersebut, gunakan formula yang digunakan ialah XR dalam kurungan B1x tambah B0. Kemudian R sama dengan kosong. Sebab itu persamaan tersebut akan menjadi B1x tambah B0. Kemudian diferensikan sebanyak 2 kali. Lepas itu masukkan persamaan yang telah diferensikan ke dalam persamaan awal. Sebab itu akan mendapat nilai B1 dan B0. Selepas mendapat nilai tersebut, masukkan ke dalam YP. Selepas itu, cari Y, iaitu Y sama dengan YC plus YP. Selepas itu, masukkan nilai yang telah diberikan pada soalan, iaitu X sama dengan 0 dan Y sama dengan 0. Selepas masukkan, akan mendapat nilai A. Persamaan Y sekali lagi dan masukkan nilai X sama dengan 0 dan Y sama dengan 2 dan akan mendapat nilai B. Akhir sekali, masukkan nilai A dan B pada persamaan tersebut.
In question 2 to Roman, we are required to find the Laplace transform of the given function. The function involves an exponent term multiplied by both sine and cosine function, as well as a linear expression. By applying the Laplace transform rule for the exponent, sine, and cosine term, we will break the function into part and use standard formula to obtain the complete Laplace transform in the S domain.
So finally, we have at the end of our presentation. So the conclusion is, this project show how second-order differential equation apply to mechanical system involving mass, spring, and damping. We explore the behavior of mechanical system under different conditions, specifically focusing on freedom motion and force motion. So using second-order differential equation, we analyze how factors like mass, m, damping coefficient beta or alpha, spring constant K, and external force Ft influence the motion of a mass spring system. Both problems were solved using analytic technique, including the method of undetermined coefficient and Laplace transform.